All right, let's work the most famous example ever, which we did in 2220, and you'll probably do it again in com theory, and you'll do it a bunch of times because it is so extraordinarily useful. And that is the case of rectangular pulse wave, and it's just a wave that has these. You could generate it using a signal generator up in the lab, and we need to understand what the spectrum of this kind of a signal is, because this kind of a signal shows up all the time. It shows up as clock signals in a computer. It shows up as pulse width modulation for a motor. It shows up as communication signals. We really need to understand the spectrum of it. So it just shows up all the time. In this case, we're going to say that these rectangular pulses have an amplitude of A, and that they're tau wide. So that's tau over 2, and that's minus tau over 2 there. And they repeat every t sub 0 seconds. And so that's our x of t. And it goes on, make ellipses here to indicate it goes on forever. So it's a periodic signal. The analysis equation is worth going into. It illustrates several things. So we're going to integrate. We only have to integrate over one full period. You get to pick what full period. So I'm going to integrate from minus t0 over 2 to plus t0 over 2. Basically from there to there is where I'm going to pick to integrate. And doing that, in that range, the only non-zero part is from minus tau over 2 to tau over 2. And within that range, the amplitude is just A. There's nothing funny going on. We've got e to the minus j omega t dt. So there's the analysis equation. And I'm going to go ahead and write this in terms of frequency. 1 over t0 minus tau over 2 tau over 2 a e to the oops, I forgot to put a k there. There's a k there and an omega naught there. Don't worry about that. I'll write it correctly here. E to the minus j k 2 pi f naught t dt. Okay, so there's what I'm going to use. There's a k omega naught there that I kind of goofed up. I should probably fix that, shouldn't I? Yeah, I'll fix that. E to the minus j k omega naught t. Okay, we're going to evaluate this one. It is equal to 1 over t0. This is an easy integral. It's we pick up the coefficient of t in the denominator, so we get a minus 1 over k2 pi f naught, and we get a j as well, and then we get e to the minus j k2 pi f naught t, evaluated from minus tau over 2 to tau over 2. And then just go ahead and recognizing we had a minus sign there, we might as well integrate the bottom limit first and then the top limit. So we get 1 over t0 times j k2 pi f naught, and then we get e to the j k2 pi f naught tau over 2 minus e to the minus j k2 pi f naught tau over 2. All right, now you have to remember little Euler's to get any further with this. Euler's identity for a sign is equal to 1 over 2j times e to the j x minus e to the minus j x. So that's Euler's identity for a sine. And you see that that's what we've got sitting inside of there. So plugging, letting x be that whole thing, right? And recognizing that there's going to be a 2j here, and it's going to cancel out a 2j there. Let's just write the final result. Let you do the algebra if you don't believe it. We get a tau over t0. I'm writing it in a special way. Sine pi k f naught tau over pi k f naught tau. You see I've kind of written it in a funny way. There's a tau here that'll cancel a tau there. So I've sort of factored out a tau and put it in the numerator. And the reason I did that is to have this argument, the sine argument, be replicated in the denominator. Now, why would I do that? You probably remember the reason for doing that is that we have a sinc function. We want to get this in terms of a sinc function, sinc x, which is defined as sine pi x over pi x. The reason to do that is it resolves a bunch of issues. This thing is not going to be very happy when we have, for example, k equals 0. We've got a sine 0 over, we got 0 over 0. But a sinc function has already taken care of that because we, using L'Hopital's rule, we get that the sinc of 0 is equal to 1. And I won't show that, but I think the book shows it. The sinc function has that, once we know that we can get it in terms of a sinc function is a very well-defined appearance. You can see that because the denominator increases, the thing's going to die off, but it's also going to look like a sine wave that's decaying in both directions. So I'll try to draw this, but I won't draw it very well. Has 1.0, 0, and at whenever x is equal to an integer, we've got sine times pi, sine times 2 pi, etc. Whenever x is equal to an integer, we're going to have a 0 crossing. There's 1, 2, 3, 4. There's -1, -2. So that's the sinc function. And so using that, we can write ck, the Fourier coefficients, as a tau over t sinc pi k f naught tau. We note that this is the duty cycle. So the smaller the duty cycle, the smaller the sinc function is. This is just the envelope, by the way. Remember, ck just shows where the spectral lines are, and they're going to follow a sinc function shape. We see kf0. Kf0 is the kth harmonic frequency. So that's that part. And we know that, again, whenever this argument, or actually there's a, okay, I just noticed I wrote that down a little bit wrong. The pi is gone, right? Because pi is built into the definition of sinc, and I wrote a pi there, so I erased it. All right, so whenever f naught tau is equal to an integer, k is already an integer, that's a place where the sinc function is going to cross a 0. So we get zeros when f naught tau is equal to 1, plus or minus 1, plus or minus 2, etc. So that's going to, or whenever f is equal to 1 over tau is going to be this first zero crossing. All right, this lecture is running a little long. I'm almost done though. These are the Fourier coefficients for the rectangular pulse wave, if you remember. Let's just plot them out. Try to make my graph as good as I can. Okay, just sort of draw an axis there, and an axis there. What we're going to get is these Fourier coefficients are going to show up if we plot like, and these are purely real, so I can put this on on one plot. I don't need a magnitude and phase plot. So let's just plot the amplitude spectrum, and it's going to follow a sink kind of a shape. Oops. Okay, so I'm gonna write that, and we can get this envelope by letting f equals kf naught. Okay, and then we've got c of f is equal to a tau over 2 sinc of f tau, right? Okay, so let kf naught equal f. And now that's a continuous variable, and really it makes sense because kf naught is the kth harmonic, but now we're just going to say f. That'll give us this envelope here that I'm showing there. Within that envelope, we have spectral lines. I'm going to make those red, or maybe I'll make them blue as well. So we're going to get these lines that show up, and their height is going to be determined by this envelope of the sinc function. Okay, so there's a tau over t. That's C0, right? And there's C1 right there. Well, actually, that's C minus 1. But because of even symmetry, that's the same as that guy over there. And this is C minus 2 right there. So we see that we get these spectral lines. It's a line spectrum. And these lines occur at 0, F0, 2F0, 3F0, etc. Okay, and this is frequency in hertz. All right, so, and the other thing we need to keep in mind is this zero crossing occurs whenever f is equal to 1 over tau. So, and this makes sense. Big, fat, wide pulses, where tau is big, we have a narrower bandwidth. All of the frequency, all the energy is concentrated at low frequencies. If these time domain impulses, I'm drawing right up there, if they're very short, very spiky, that requires high frequencies. So tau is small. That means this zero crossing is way out there. And that's why this is referred to as the spectral bandwidth of this pulse signal. Okay. Anyway, so that's the approximate bandwidth. So this is the spectrum that we'd see, the amplitude spectrum for a rectangular pulse wave. It's a line spectrum. The distance between the lines is equal to the fundamental harmonic. That's the first thing you got to know. And the bandwidth is inversely related to the width of these pulses in the time domain. And that's a fundamental result, that the width in the time domain is inversely related to the bandwidth in the frequency domain.